dynamic universe model by Dr. Tuomo Suntola. And of course, Dr. Suntola is known that he actually 50 years ago invented the atomic layer deposition, which means you can put atoms one layer at a time. And as far as I understand, it's what makes this into a computer. So I always felt, okay, he knew how to do that, so maybe he had to give him a little bit of leash in cosmology and see these new ideas that have been developed for a long time. And of course, as a new approach, this is again where it's important is that let's try to understand what it means. I mean, I've been trying to do this for a couple of years now because we have this kind of project where we study both the Bohm-Hailey program and then also the universe program. And I'm finding very exciting, once you understand how the model works, it actually can be very, very exciting and you get a real sense of it. But then again, I'm not able to really evaluate the broader and deeper relevance or how correct it is. And this is, of course, we have here other people who are much better to do that. Okay, well, please go on.
Thank you, Paul. So my title and my talk is titled Relativity Observations Support Zero-Energy Dynamics Universe Cosmology of Lambda, C and Cosmos. The presentation is based on a manuscript draft I have made together with my colleague Petri Leevonen, and many of you have received that already, and if not, it's available here on Physics Foundation's homepage to download it. Okay. So, the overall possible solutions, let's look at the problem and the challenge. Single impactful image showing the early massive galaxies with a question: how did these form so quickly? So we can look at, see that the small, sorry, okay, the small dot. Doesn't work. No.
Maybe it has no battery and it's also not strong.
Oh, anyway. So, how is rolling out and many similar ones challenge our understanding of the universe? Some empirical conclusions, early galaxies. So this apparent universe framework, there was high energy state enabling very fast development of galaxies in the early expanse. So that's a big difference with the present field. Angular sizes of galaxies suggest local expansion with the expansion of spherical space as the whole. So on the other hand, data on the number of days and months in the year that are stored in ancient coral fossils and sediment sand support the expansive solar system as well. So two kinds of data are available in the correct. No. Okay, I would like to use the mouse here. Okay. Then further empirical conclusions comes from supernova observations, which have been observed for the last about almost 30 years with high accuracy. And supernova magnitudes in this dynamic universe framework can be explained with high accuracy without dark energy or other extra parameters. So that's what is there. And what is also very important, especially for black holes, is that the overall zero-energy balance, which is the basis of the whole theory, allows slow orbits near the critical value, which are then able to maintain the mass of the black holes. So there is a possible solution, what keeps the mass of the black holes. And which comes directly from the basic structure of the theory, so there's no extra ideas in that. So let's first look at the energy evolution in the free sphere space. So the idea of the free sphere space is a very old one. There are several scientists in the past who have been thinking about how to get out of the edges of three-dimensional entity. And the most natural way of doing that all is to close it through the fourth dimension. This was also, as many of you certainly know, the first idea of Einstein for explaining the cosmology behind general relativity. And because at that time it was generally quite clear that space itself is static, he needed to add the famous cosmology constant, which then was taken as dark energy to correct the supernova curves. But as soon as we accept that if we are mass divided into a spherical structure, it tends to shrink towards the center of the system. So if nature is going to do that, let it do it. And that's the basis of the dynamic universe theory. What it means is that starting from practically, if we like, almost infinity in the past, the structure finds its mother center at the center of the spherical structure and wants to move against the center, which means that we are converting the gravitational energy of the system into the energy of motion. It goes to singularity or turning point, and now we are expanding and we are paying back the energy that we got from gravitation. So it's very simple. In fact, the rest of the whole story is a kind of double entry bookkeeping of energy. So we maintain the energy balance of the system by taking care that any energy motion is obtained from somewhere, so that if you get something, it's out of something. Very, very clear and simple principle. And in fact, when we find out that the energy of expansion MC to the second is, which we call the rest energy, once we are moving with the space, is in fact from let's say general coordinates. When we look at it from the total coordinate system, it's moving at velocity u in the direction of the radius. And for this simple equation, by applying the best language for the total mass of space and the Hubble curvature, Hubble radius, and the gravitational constant, we get 300,000 kilometers per second, which is exactly the velocity of light. So it means, as stated already, that the rest energy of mass is obtained as the energy of motion from the release of gravitational energy in the contraction phase, and it's now paid back to the gravitational energy in the ongoing expansion phase. So if we compare that to the present understanding of the start of the expansion, which started from the instant appearance of energy and the start of time and the laws of nature, first we extend the time coordinate to the infinity in the past, and we start the development from there, and now we build up the energy, and then we release the energy. And what is the very important extra plus here is that with these simple formulas, we get exact, very precise, and mathematically simple equations for the development of the radius of the sphere and also the time which has been used to reach the present radius. And in fact, the present radius is 13.8 billion light years. The time needed to that due to the faster expansion time in the early times here, it's 2/3 of that, which is 9.2 present years. So that we have to be careful with stating that also the length of a year has changed during the development. And in fact, that's exactly the same number what was obtained before the dark energy was added to the equations. So that's the constant simple expansion which gives the same way, which was based on the conservational energy. If we don't compare the development of the energy during the expansion since the start of the expansion here, according to existing model, it has been essentially constant. So the M total mass and the velocity of light c are assumed to be constant. However, at the same time, the gravitational energy has changed remarkably because the volume of the structure has been changed. But what is specifically interesting is that also, according to the Friedman solutions, when we applied the critical mass density condition, which is considered to be the case today, there is the energy balance, however, in the form half times mc to the second is equal to the gravitational energy of the system. The half factor half comes from the boundary condition in the field equations, which means the Newtonian space in low gravitational conditions. However, the difference is quite different. The situation is quite different here in the random universe development. Now we maintain the balance of the gravitational energy and the energy of motion, which is our rest energy and energy of radiation, which means that in the early expansion here, the energy, kind of energy excitation between the released gravitational energy and obtained matter energy has been orders of magnitudes higher than it was today, which gives a very natural explanation to the first galaxy formation in the early universe, which is very difficult to explain with this. The inflation period here can't help in that because it was only a small fraction of a second that was assumed in the start of the expansion. Okay, let's do some key consequences when changing now the framework of mind. Instead of constant c, we have varying c, because c, the maximum velocity in space, is necessarily linked directly to the expansion velocity in the fourth dimension. And that also releases time to be handled as universal coordinate quantity. And we'll come back to this in the next steps. So that also already as seen in the previous slide here, in the early expansion, the speed of expansion was much higher, and it also meant that the velocity of light and all physical processes were much faster than they are today. So that there was accelerated development. We don't need specific Big Bang in order to create the rest energy of matter and matter, because that has been there for all the time. So the whole development created the energy and the mass was a kind of kind of energy carrier or a substrate for expression of energy, which we are going to discuss more in detail tomorrow, which is a very important part of the essence of mass. We don't need any inflation, we don't need dark energy. And what is very important, no one is related to the rest of space. As we look here, the mass, local mass n, it's all the time, it's in gravitational interaction with the rest of space, mathematically easily expressed using the mass equivalence of the whole space here. We are going in more detail to the ratio of global and rest of space. Also, what is very important is that inertia is not a property of mass as it was in classical mechanics, and also it's a kind of property of mass also in the relativity framework. But inertia, now we can understand inertia as the work against global gravitation. If you think about any motion in space here, it's central motion relative to the center or center mass in space here, which means that the central force created by the motion compensates part of the gravitational interactions. And when we look at that in terms of energy, we can find that the energy net inertia can be expressed exactly and mathematically precisely as the work done against the gravitation of the rest of space. And this is exactly the last principle. And then relativity. Instead of expressing relativity with kinetic time and or space-time conversions, relativity can be expressed as locally available energy. And in fact, it doesn't need a specific relativity theory, but it's part of the total structure of the field, or the basic structure of the field, so that we can find that once everything in space is linked to the rest of space. The relativity is not primarily relativity between an object and the observer, but it's relativity, primarily relativity between global and the rest of space. And we will find that there's a system of nested energy frames which links the local finally to a hypothetical state where all must be present at the homogeneous space. And that's in fact the frame we this morning already heard about. Chris talked about the non-observable hypothetical reference frame for any frames in space. Okay, then let's look what the relativity means. How can it be concluded locally? So in Minkowski space, at the time, last century, when it was assumed that required that space itself is static, the fourth dimension CD, although CD has dimensions of meters, C is meters per second times seconds, it's meters, it was called the dimension of time. As soon as we notice that this the fourth dimension is the dimension of the radius of the spherical closed space, it means that we all, instead of having a state of rest, we are moving at velocity c in the fourth dimension. And what follows is that the mass assumed to be at rest in space is not at rest, but has momentum mc in the fourth dimension perpendicular to any space direction, when we let momentum be in any space direction, the total momentum becomes the orthogonal sum of these two vectors. And what comes from here, as we use, we can express the energy here as C times momentum, and we get directly the relativistic total energy of motion in the Dirac formulation, which has the scalar value equal to that one, which was already disclosed in Einstein's 1905 paper. So we can find that now we find that the relativistic energy, the total energy is obtained without any assumptions tied to the theory of relativity. But we go further with this. Once we study the energy balance between the motion and gravitation, and find out the inertial work, which now can be identified as the imaginary part of the complex rest energy. We like to express that in complex form. It means that the rest energy of an object in motion in space is reduced by this same factor, Lorentz factor, as which explained by using time dilation in special relativity. So now also it means that the ticking frequency of atomic clock is reduced when the clock is in motion. In layman language, we can say that the ticking frequency of a moving clock is increasing because it uses part of its total available energy from the motion, which means that it has less energy to run the clock as in internal energy. And mathematically, it's exactly what happens. So now we saw that in fact we can find as soon as we notice that we are not at rest, but we have the motion in the fourth dimension, then we don't need relating time or drift construction in order to explain special relativity. So let's see what's the role of gravitation then on the force and the energy. So this is a kind of starting situation. If all mass is at rest in space, the only momentum mass has is the momentum in the fourth dimension, so related to the expansion of the sphere. So the next question is, how can we conserve this energy? So this is all the energy which is available in space comes from this particular energy. So how can we have energy and motion in a space direction without breaking this whole unity here, which is considered the total energy of motion and energy of gravitation. And nature is very cleverly doing that by bending space close to mass centers, which means that we are now dividing the original C0 into orthogonal components. One is the momentum or velocity of free fall, and the other is the local rest momentum. And it means that the local fourth dimension is now bent by the same angle here as we have bent the space. And with very simple calculations, we can then create equations where we can determine the change of C in terms of the loss of total gravitational energy. The same procedure may then occur in several steps, which means that we are now going to work a structure where this local energy here is related to the parent frame, which shows flat space in this, and here in the next step we are relating this local energy to the space in this dimensional direction. So how does that differ now from the from obtaining velocity.
No. Okay. When we obtain velocity at constant gravitational potential, then we need to bring extra energy into the object accelerated. And it can be expressed with terms c times delta, or delta m times c to the second, or as we can see here, it's necessary to make a difference between velocity of light in homogeneous space and the local velocity of light, which is a little bit smaller. And in Earth conditions, we can estimate that the difference between these two velocities is of the order of ppm, 1 part per million. And in fact, the c to the second should be written as c0 times local c. Let's see the consequences. We can see here that we brought kinetic energy in form of mass substance or mass energy carrier to the object accelerated. In this case, we don't need to take extra energy, and in fact, we have received our kinetic energy against a reduction of the local rest energy. And what it means is that in fact, that means infringement of the equivalence principle, because these two ways of obtaining velocity is not equal, although they are very close to each other in low gravitational field, as what we have on the Earth and near Earth as well. So let's see further consequences. So here I already mentioned that we can see the Mach's principle here. So that was the work that reduced the rest energy of the moving object and also affected the clocks in motion. And here, when we add now the effect of gravitation and motion, I haven't written the details of the equation, but this is the gravitational factor times mass divided by rc to the second, and this is the velocity factor, 1 minus v divided by c to the second. And we can find out that also the frequency of atomic clocks follow the same. And it means that we have this kind of formula for atomic clocks, which has both gravitational factor and velocity factor, which can be related to Schwarzschild solution, which has these two factors under the same square root here. And in Earth conditions, the difference between these two is of the order of 10 to the minus 18th, so that it's very small difference which we can find between these predictions in near-Earth conditions. Now, when we follow the build-up of local mass centers in different steps, we end up to the system of nested energy frames, so that we can see that the effect of the rest of space is reflected in the rest energy of any local object we are studying here. In our ion frame, we have reserved some part of energy here to the motion we have with the accelerator in the rotating Earth, then Earth rotating the Sun in the solar systems, then solar system going around the center of the Milky Way, and so on. So that basically here we have now combined the idea of local frames and the whole energy structure with now absolute rest frame, which I have called the hypothetical homogeneous space. So let's summarize at this step. A fourth dimension in special general relativity is related to time. In du, it's spatial meters. Although in a dimensional analysis, if we make it by accepting that c is not something more physical than undimensional, not the dimensional factor, we have fourth dimension metrics as well. Speed of light is not a constant, but it's related to it's fixed to the expansion velocity of space. Time is not relative, but it's universal. Instead, clocks and physical processes runs lower due to motion and local gravitation. So that it finally question or switching the direction we are looking at. Relativistic effects, well, they are derived kinematically originally, which is very, very understandable, taking into account the status of general understanding of physics and the universe at the time when relativity theory was created. And now our relativistic effects can be related to the locally available energy. Equivalence principle, here it's exact in general relativity, and it's approximate, which works well in a weak field, but which doesn't work in high field. And that's the key why we are my interpretation here is that the reason we don't have stable orbits close to the critical radius of black holes comes exactly from this thing. So that when we follow the conservation of energy, we can find out that we can't, we are the maximum we can get converted is the rest energy of the object far from the black hole, and we get nice slow orbits near the black hole. I have sorry. Exact then energy in acceleration. Yeah, we find that external energy input and in dynamic universe in free fall we have the rest energy conversion, which doesn't add the energy of the falling object, and that's the big difference. Okay, then observational evidence. Let's see what we find. Major galaxies. And that's what we already discussed. If we call a little bit more precise, if we are a little bit more precise here, the collapse factor can be related to the redshift, which describes the status of the universe we are looking at. And it means that when Z, the redshift is 10, which are the typical galaxies now found with the James Webb Telescope, the factors, speeding factor is 3.5. At redshift 100, in the earlier phase, it was 1,000 times higher, and when Z was 1,000, which is about the redshift at expected emission of the background radiation, it was 32,000. And in this picture, we could, here we are. We found the high energy state here in the early development. And now this is very interesting. And this is the observed angular sizes of galaxies, quasars, observations. So I have picked from Loviagin paper. In that paper, all the black dots and also the red blocks, which present the observations by James Webb Telescope, they are collected in this general chart in common. And we can find out that the prediction of of existing theory requires that we are under this pink area in the left-hand side picture. In dynamic universe, the development is Euclidean, and what is the interesting point here, we can find that there's a very strange peak, and it means that we are now looking back to redshift about 22, which means that we are looking to the opposite side of the spherical face here. And it means that also either side of that point we should be able to look the same object this way and this way. And if this galaxy candidate, which has redshift 31, it's not confirmed to be a galaxy, we end up with, we should have the mirror picture at redshift 15.7. So that's extremely interesting if we are able to find such a pair of observations from one and same object at opposite exactly opposite directions. So I hope we'll see that someday. What it means that here, the reason that the standard prediction turns upwards here comes from the reciprocity principle, which was presented by Etherington in 1930s, early 1930s, and which was originally based to the idea of special relativity, to have the same angle as what had occurred at the time when the light was emitted. And the other very important factor here is that we need, for the Euclidean behavior here, we need to assume that the objects are expanding with the expansion of space. And in dynamic universe, where everything is linked to the whole, it means that the conservation of energy means that the expansion of space occurs in any gravitationally bound systems also locally. Relativity, which is local theory, requires local conservation, which means that it requires that local systems do not expand, because otherwise they are losing energy, gravitational energy. That's a big difference. So we get some additional evidence, surprising additional evidence from ancient coral fossils. Coral fossils and sedimentary tidal rhythmids have conserved fingerprints of daily, monthly, and annual variation in the samples. The development of the number of days and months in a year can be calculated back to hundreds of millions of years. My colleague Heikki Sipilä, who is sitting here on the first line here, made excellent work in finding out the data and made the basic analysis for that. And it turned out that for understanding that the observed number or development of the number of days necessarily requires the change in the length of the year, which requires that the local system is expanding, solar system is expanding with the expansion of space. So in standard prediction now, there's only factor is the tidal effect, which affects the rotational velocity of Earth and the length of the day. But the length of the year is assumed constant, because the solar system is assumed not to expand. And in DU we have these two effects. These are the fantastic samples. So black vertical line here is the time backwards 800 million years back. And that's the number of days in a year. The tidal friction prediction gives this kind of curve. When we add the effect of the lengthening of a year, we come exactly to the samples. Interestingly, when I made this calculation from Heikki's samples data, I didn't know what is the generally accepted tidal friction effect. So I stated that in order to fix the curve to the samples, it means that we should have tidal friction about 2.5, so that it came other way around with nice accuracy. Conclusion: coral fossil data gives strong support to expanding solar system. And the other was the sediment samples for the length of a month. I don't go into detail here, but I can show the two curves here, so that if we are using Hubble constant 74, we have the upper curve prediction, and with 66, the lower curve. We can see that we get very similar result as we got with the coral fossils. Also, what is very interesting here is that the expanding solar system gives a natural explanation to the faint young sun paradox. So 3.5 billion years ago, Mars was almost 30% closer to the sun, which explains the liquid water, and in spite of the about 25% fainter solar insolation. So that it's a very natural possible solution to the problem. So we stated that standard model predicts non-expanding local system, DU predicts expanding local system, JWST observation of the angular size of galaxies support the expansion of local system, and several independent observations like the coral fossil and tidal rhythms and ancient solar eclipse also, which I did show here, support the expansion. When interpreted in general relativity framework, lunar laser ranging and transponder measurement of planetary distances negates the expansion of the solar system. When interpreted in DU framework, lunar laser ranging and possibly the transponder measure, I already thought that I found the solution, so-called Einstein effect, which explained the difference in the interpretation, but it needs more work to be done here. But it's a kind of precise work we need. So let's see the supernovas. So the standard black points are observations, and what is interesting here is the latest high redshift sample, the green star here. And the standard prediction is the blue line, which is under the observations, and the equation which it's based on is here. Now, if we compare the DU prediction, which is a very simple equation, we can see that it here in the long run it completely fits with the observations and also the standard prediction. But here it gradually deviates upwards, and if we look the upper part more precisely, it's very promising. But unfortunately, there's only one high Z sample now available. But I think in near future we get more of those. Magnitudes of supernovas were interpreted in present framework. The prediction fitted with dark energy matches observations, which are transferred to emitter's rest frame. And here we are again, we get a very important effect of the handling of the data in the framework we are working in. When interpreted in DU framework, the prediction matches bolometric observations without fitting parameters. As you notice in the earlier slide here, there are no parameters at all. There's only, you can see that the essential term here, it already only has the redshift instead of the dark and energy and and normal matter factors. When interpreted in DU framework, predictions matches bolometric observations, which are in principle direct observations when we have our filter match to the redshift we are observing. I don't go into details here because time is running, but I like to show you this. In standard prediction, which comes from early 1930s, there are two effects which makes it different from the DU prediction. We have power dilution here twice, which is a kind of lengthening of the kind of Doppler effect, and then the Planck, the interpretation of a Planck effect in dynamic universe, and that's what we are going to handle tomorrow in my talk, is why we shouldn't add the other factor due to Planck equation, is that when we write Planck effect, instead of saying it's h times f, we can equally write it as h times h divided by t, which is the cycle time. So in a cycle time, we are conserving energy in the cycle time. Cycle time is changing, but not the energy. And that's a very important thing. Fortunately, I found a table of direct observations through each filters. And here we can see that we get the bolometric curve by following the optimum with each filter. And it means that the reference for bolometric is here. Now let's see how it fits with dynamic universe. We have the bolometric here. Dynamic universe prediction is exactly here. When we add the standard prediction to the bolometric, we'll find that it makes certain difference. And the reason is given here. In lambda CDM practice, observed magnitudes are converted to emitter's rest frame with K correction factor in addition to filter mismatch correction adds factor 5 times 1 plus z to the observed magnitudes. And I have went through that in detail, but we don't go it just here. But when taking this into account for making the DU prediction for the co-corrected magnitudes, we write it here in the lower form. And then there's the co-correction, and here we go. Standard model without dark energy, and then the finding of dark energy, which matches the curve here, and DU without any dark energy or other parameters is here, and gives the nice match. Black hole orbital dynamics. When we follow the orbital velocity and escape velocity in general relativity framework or Schwarzschild framework, we can find that when we go down close to the critical radius is here 1, and the radius we are studying, the number here is 10 times critical radius, 20 times critical radius. When we go to 6 times, or 3 times Schwarzschild critical radius, then the orbital velocity exceeds the escape velocity, and that's what I interpreted to be due to the equivalence principle, which requires the energy, extra energy for in kinetic energy, making kinetic energy. In DU, the situation is different. The orbital velocity stays below the escape velocity, and here we have the slow orbits. Now we have the critical radius, which is only 1/2 of the Schwarzschild critical radius, but we have very nice slow orbits here. There was one very interesting observation from Sagittarius A at the center of our Milky Way. They observed rotational periods were 16.8 minutes, which was surprisingly small value. With Schwarzschild black hole, the minimum is here. It doesn't give orbits below. Sorry, losing my mouse. Oh, here we go. Here. But when we look the prediction for period in dynamic universe, we get an extra factor here in the square root, and it gives a curve like this, which matches very, very nicely to the values here. So let's make some summarizing. Special and general relativity. Speed of light is a fundamental constant. Time and distance are relative. Space-time curvature explains gravity. Equivalence principle is central in the theory. Universe appears same to all observers. Pay attention to the last statement. Speed of light in dynamic universe. Speed of light varies with expansion and also locally. Time and distance are absolute coordinates. Energy availability explains relativistic effects. No equivalence principle, and same universe for all observers. There is now only one universe. No, its observer don't have specific universe for them. And now, finally, is it time for a paradigm shift? JWST observation seems to favor DU over lambda CDM predictions. Cosmological evolution in DU occurs without Big Bang inflation or dark energy. Testable predictions distinguish DU from standard model across multiple domains. Single coherent framework calls for serious work on novel and grand ideas, and that's why I'm expecting for any one of you in this audience. And what we can offer is a physically intuitive alternative based on absolute time, absolute space, and energy conservation, showing the possibility of unification and clarification of theory structures. And that was our message. And thank you so much for listening. In fact, can you repeat the question?
You haven't. The question is that you haven't included any quantum mechanics.
Sorry. In this presentation, I don't have quantum. We have to wait until tomorrow.
A couple of questions. What happens at the singularity? I'm slightly worried that the singularity.
I'm slightly worried that the singularity, it's there, but we don't know exactly what happened. What makes it? Sorry.
Paavo, please come here. I really can't follow your speech because the echo changes. So the microphone makes it worse. Yeah. Yeah, it's better, but maybe I need your help.
What happens, because you show the singularity,
yes.
You say it's not the Big Bang?
No.
But what's happening there? Because
the contraction turns into the expansion. It's a kind of turnover. It's a kind of turnover. I don't think it's not like this, but I think that we are passing just the middle point. Like hyperbolic. We don't need any Big Bang then, because now now tomorrow we are discussing the concept of mass, and we can find that mass can be seen as a wave-like energy carrier rather than particles. Mass is not necessarily particles. The mass, most probably, and that says has waveform. It appears in the form of waves, and then we can consider that we are not getting closer than a wavelength in the turnover point. But that's speculative, so I can't guarantee, and there's no experiment for that.
Another small question. You have several parameters. You have a 0.6 in the formula for the year length.
Yes.
You have 5, 10. Where do these come from?
Because when
you calculate the year length,
year
you
length,
have a number 0.6, 0.6.
Well, obviously, goes
This is only
When you, in the formula you have for the year length.
one energy goes and if that's
And then in the magnitude you also have 5 over 10. Just wondering where yeah, there. So you have 2.5.
yeah, that's the effect. It comes from here, the length of the year, the effect of the length of the year.
Yeah,
That gives the 0.6.
but that's calculated or that curve for the length.
It's calculated from the expansion speed, so the expansional space. So that we are in that we assume that the solar system expands in direct proportion to the expansional space, and from that we then get the
And is that a
curve.
constant expansion then?
No, it's not expansion, but we know exactly how it develops from the.
Okay, because you're not going that. Still going to want
Yeah, but the calculation is not shown here. That's the result. But you can find that in my book if you like to hear that.
Okay, well, that's all.
Yeah.
Okay, thank you.
Yes.
Any other?
Yeah,
Yes, yes,
yeah,
Callum?
what I was,
No, actually,
sorry, Paavo.
Yeah.
I was adding that in principle, Petri had prepared some mathematical demonstrations of the black hole vicinity, so that we have time for panel discussion here, and if we like to see, okay.
we can have still a couple of
Just a very short question. I know you said quantum is tomorrow.
Paavo, yeah.
So I will try to speak up. Yeah, I know you said quantum theory is tomorrow. Unfortunately, today is my last day. I have a very short question because your system is holistic and it's closed,
Yes.
as is David Bohm's system. I want to ask: is there non-locality here as well? Entanglement also in dynamic universe? Do you mention non-locality and?
Yeah. Well, that's very important and big question indeed. But perhaps you paid attention here that everything in dynamic universe space is connected to the rest of space. So there's naturally a kind of immediate interaction. And if we like to accept Mach's principle, the mechanism of gravitation must be understood as sensing the local gradient or local gradient gravitational potential, so that the sensing event doesn't have any long-term interaction, but it's there, it's local, and that's very important.
So non-locality is in the system. It is built in the system.
It's built in a system, yes.
and then we have also Callum Robson back there, breaking blown up.
So a couple of slides ago, you had the two graphs comparing the lambda CDM and
Yes.
the DU energies. So I was just wondering which, I think it's slide 3. So it was one where you had like the two copies of bolometrics for the DU energies doing like this, and then you have the straight line MC squared and the slide 3, I think.
Let's go back to the
Go
back to this.
I think that's the third slide. So keep going. Yeah, sorry. The inconvenient distance.
You can hold the button
Yeah,
down.
that one.
yeah.
The next one, sorry.
Yeah.
The one before.
Right.
So
Forward.
Number 4. Yksi takaisin vielä.
Eteenpäin.
No.
No, people.
Vielä
Next one.
lisää vielä.
One more.
one more.
Vielä.
One more.
Siinä.
Yeah.
That's it.
Yes. So, thank you. So I was wondering, what is the gravitational energy in that star?
What is the
gravitational energy?
What is the gravitation? It's the energy that is calculated. We first integrate gravitational energy for 1 point throughout the spherical spherical surface, and from that result we get the total gravitational effect, and from that we define the central mass equivalence.
But how are you defining it in the lambda CDM case?
Miten siinä lambda CDM?
Because there's issues in how you define energy.
I'm not the right person to answer that question. It must be given to lambda CDM people. It's a quite tricky thing, but the approximate value in some books at least are given as if it were a three-dimensional filled sphere, ball filled with mass, so that it's different. That's why as you may pay attention here, that I have not given a mathematical expression here. But basically, you can understand that when the density is small, the gravitational energy then is lower, because it mathematically is looked as negative as released energy. Yeah. So that I can assume that the curve is roughly the same. At least it's not equal to the blue line here. It's something like this. So that I take responsibility only of this part of the picture.
The energy you have there is this the T00 component of the stress energy?
So the E00 component.
T00. Is this the T00 component of the stress energy tensor?
The T, like
Yeah.
The stress energy tensor T00 component.
No, sorry, E00. What is it? So C, you say C0.
Stress energy tensor. T00.
Oh, I see. Okay. In energy tensor, that's you mean the rest energy component.
Yes. So on the right hand side of of Einstein equation, you've got T0, you've got T mu, which is the split energy. So I'm just wondering exactly which bit of that you're using here for the energy in the relativity.
Se stress energy tensor ja kiinnostaa sitä tässä.
In my calculation, I'm not using that. In a way, I don't need that. Then, at least I haven't used such tensor presentation, because I can use algebraic formulas for expressing the whole thing. But in a way, if I look the stress energy tensor, think about in its simplest form, that it only has the basic force in 3 dimensions, from 3 directions, so that in a sense it describes, we have the 0, 0 element is a kind of volume element, which is which can be converted as the force integrated around a volume unit is equal to the energy inside the volume. So that's what it physically means. And certainly there's a very nice connection then to the dynamic universe, because the sum of the three space direction forces, in a way they describe, we see the rest of space, the total force is zero if we have in a way it describes that it must be spherically closed. Let's say it needs the spherical symmetry, let's say it that way. So it tells something similar, but I'm not familiar. I haven't gone deeper in studying the differences. Yes.
Yeah. Okay. So you say there are 4 spatial dimensions. Is time one of those?
No. Time is time. Time is different from the space directions.
So
Time is time. You can rather consider that as a scalar.
So, like 5-ish then dimensions in total? Are there, like, if you do, like, for some reason decide to call time a dimension, that means there's 5 dimensions.
No, you may call it the fifth dimension then, but it can be put in the same coordinate system. It's not a space-time. Time is time, and space is space.
So we're on some subset of at this time we're on a subset of a 4-dimensional space.
Yes.
What determines the shape of that subset? Is it like, does it change over time?
Yeah, time is it's a coordinate which we need to express velocity or change the speed of change. In dynamic universe, time itself is not a physical. It's not a physical phenomena. Physical systems have certain rate, and time is the measuring background for comparing speeds of rates of physical system and speeds and so on. I'm not sure that I can explain it.
Or you want to continue?
I was wondering, related to that, because you relate your capital R, your expansion.
Yes.
Now, it's not time implicit in expansion when you talk about the expansion?
Yeah, we need the concept of time in order to.
Yeah, I mean, when we say, 9.2 billion years.
Yes.
Clearly, we're talking about something related.
Yeah,
So implicitly, time is in the background of your 4th dimension.
In my thing, now we are in a very, let's say, usual, very typical problem in thinking and expressing our ideas in different frameworks. And for me, I've been working with dynamic universe frames for such a long time that it's quite a task for me to try to convert my thinking to general relativity or special relativity, because my very first trigger for starting to work to find this kind of to get out of the relative time. So because as my background is in technology, and a technologist, it's important to really understand the physical effect. It's not enough to describe them correctly mathematically, but we need to understand how they work. And that's why I couldn't accept the concept of time in relativity theory. And that happened more than 50 years ago. But it took, I was touched fully in technology work for several decades. So then mid-19th, I understand for another trigger that the only way of getting out here is to understand that we are not at rest, but we are moving. Then we don't need the relativity of time, as I demonstrated here.
Well,
yes, it's very much what Copernicus make that.
You're using the word "we are moving."
Yeah.
As you said already.
It's time for you're moving.
Yeah. No, I agree.
So time is time, and clocks and other things, they run at different rates depending the state of motion and gravitation. And the reference for the motion is not the observer, but it's the state where the energy for the motion is set. So that the source of kinetic energy determines the reference. And that's what leads to the system of nested energy frames, where we know exactly how they are related then to the rest of space and to the hypothetical homogeneous space.
Yes. I don't know if it would be helpful, but I was thinking about this dynamic universe, and there's a sense in which it assumes that there is like an absolute time, and then I asked Tuomo and Petri, so is there a clock that's ticking in this absolute time? Because all the other clocks are ticking at different rates depending on the energetic environment. And I was told that you have to go into the middle of the galaxies, imagine a clock there, and that clock would be somehow, no?
No.
Okay, well, tell me.
No, you should go to the first, clean all the galaxies and other structures in space to make all mass homogeneous, divided uniformly in the whole space, and then stop any motion there, and then put your clock. But it doesn't. The clock, it's as a mechanical equipment. It needs something. If you divide all mass, you also have to solve your clock.
Yes, so in some sense, the absolute time is it measurable?
No, for me it's a wrong question, because.
But Avril loves absolute. Is Avril here? He loves absolute time. So
because for me, one of the key questions in going ahead in the whole thing was that for first, science is for making nature understandable, and we don't understand anything if we can answer the question what, where, and when. They are, and it's not a coincidence that mass, meter, second, and kilograms are the base units in the system of units. Very interesting, philosophically.
We have here a question. Yes.
So this three-sphere, is this three-sphere completely flat then, apart from the curvature of the sphere itself?
So once again,
is the three-sphere flat apart from the curvature of the sphere itself? So like mass does not curve the three-sphere?
I simply can't understand.
Flat three-sphere.
That's whether we say that Friedman's critical mass means that space is flat, which is a very strange statement because it means something like Euclidean environment. Locally it's fine, but mathematically the other interpretation of critical mass condition is just a zero energy condition. And that's what I use.
So related, does mass change the curvature of this three-sphere?
Yeah, the three-sphere, when mass is accumulated, it then creates the local dents in the space. So the picture is very much the same as what we described for the time space-time geometry in general relativity, although it's not called.
I see. So like a black hole or something that's going to put a huge dent on this, but the whole thing is still expanding outwards.
All the system, all the sphere is expanding, and the expansion can be solved from the zero energy condition.
Okay, thanks.
Okay, now we had actually scheduled a panel discussion for 3 o'clock, but in the true spirit of the workshop, as there were questions and I thought, well, let's hear them. But we have still 25 minutes, and we could, if Chris, Yvette, Petri, and Tuomo, after all, we brought all the chairs here, and we had to do some work.
Okay.
So you could come here, and maybe you could make a short comment.